In this demo, we will introduce the time series imputation for GAN algorithm. And for a more intuitive display, we will carry out web application visualization. As Andrew says, data value drives the algorithm learning process. Therefore, obtaining larger datasets is one of the most reliable ways to improve the performance of algorithms, and data augmentation is necessary. There are many existing data augmentation methods, among which, with the development of artificial intelligence and deep learning, generative adversarial networks, which also be called GAN, have shown excellent performance. The basic idea of the generative adversarial networks is to train two neural nets, a generator and a discriminator, to compete with each other and improve their effectiveness. The generator needs to convert the input conditions, like partial images here, to the realistic one, while the discriminator is to train to distinguish whether the image is genuine from the real world or painted by the generator. This computation-like training encourages the generator to produce visually appealing images with high realism. However, existing GANs are usually applied to generate images for generating time series, which often ignore the temporal dynamic features. Therefore, we propose time series imputation generative adversarial network, an algorithm based on time series generative adversarial networks. This is time series imputation generative adversarial network, combine unsupervised and supervised learning to capture both dynamic and static features of time series. Construct potential space using embedding network with stepwise supervised loss. Joint training the embedding network and the GAN. Replace the traditional GRU with GRUI. Use denoising autoencoder to form generators for missing value imputation. First, we introduce an embedding network to provide a reversible mapping between features and potential representations. A potential space is also provided in which the adversary network operates, synchronized by supervised loss. Then, for GAN, we use the gated recurrent units for imputation, which is GRUI, and denoising autoencoder. GRUI is derived from the traditional GRU, and since we use this algorithm for imputation in missing values after data augmentation, we introduce a decay factor, beta, to obtain its essential features and missing loss, which enables GAN to handle missing time series effectively. Since the traditional idea is to find the optimal vector day for input and filling after training the GAN, we found that the denoising autoencoder adding noisy step simulates the missing values well. So we use it for pre-training and fill directly to generate the complete dataset for input. For the discriminator, it mainly consists of GRUI and fully connected layer neural networks. The GRUI is responsible for processing either complete or missing time series and performing discriminative output. Thus, the whole algorithm training process is as follows. Train the autoencoder to optimize the reconstruction. Optimize supervised loss to capture temporal dynamics. Joint training for data augmentation and missing value imputation. Then we will go to the web application of this algorithm. To better demonstrate our T-GAN model, I built a deep learning application using the Streamlit framework. Give users more intuitive presentation of our data and results. First, this is our homepage. In the homepage, we briefly introduce the innovation of T-GAN algorithm. You can click here to get more information. It also introduces the related work, and you can follow the link to see the paper to learn. Of course, if you have any questions about this model, please feel free to contact me. You can enter your name, email address, and message here and send it. Then we go back to the application. First, we need to upload the dataset. You can choose any dataset to upload. Next, go to the Explore the Dataset page, where you can choose whether to show the raw data. If you click to zoom in, all the information in the dataset will be expanded. You can also select the length of the time series, Drag the button, and the time series start and end time will feature the dataset. You can see the change in the following picture. You can also select an indicator of the data you want to show. You can zoom in and out, move your mouse over the line, and it will show you the details. You can download and save this image when you have the local information you want. After that, let's enter the training visualization page. We transformed the training process into interactive demonstration animation. These are GAN's 3 training phases: embedding network, supervised training, joint training. And at the end of this page, we added the algorithm comparison and the parameter analysis. If you choose it, the results show the GAN significantly better than time GAN. If you choose that, you will see gamma is important to the model. What's more, in order to study the role of each part of GAN, we conducted an evaluation experiment. We gave the overall comparison result, and GAN is clearly superior to other methods. When you select GAN, the trained model is loaded and called, and the synthetic data is generated for PCA and TSNE qualitative analysis. The resulting images can be interacted with, and you can zoom in for more detailed analysis and save. The same goes for other parts. The last part is to fill the missing values with GAN after data augmentation. We compare 3 evaluation indicators for various filling methods. You can click on the icon and select a metric for comparison. What's more, we give more information about different methods. When you choose different methods, it will generate corresponding results in time. After the local setup, we deployed the interactive deep learning application to the Heroku web application distribution platform, which you can access at tgan.herokuapp.com. This is the end of the demo. Thank you for watching.